Welcome back to probably what most people think of when they think of chemistry, the periodic table. Okay, so we're going to talk about the periodic table and periodic trends and how you can predict certain properties of different elements by looking at where they are in the periodic table. Okay, and so what I'm going to show you here is an image of the periodic table. And so the original periodic table changed over the years, but probably the one that we are more familiar with was the one that was done by Mendeleev. And here's what his version of the periodic table more or less looks like. You can see that going horizontally, you have periods, and going vertically, you have groups, and there's about 118 different elements represented in this periodic table. One thing that is a little bit exciting that I want to share with you is the periodic table that you may have seen before in different textbooks is actually outdated. Okay, and so in the past couple of months, literally about a year ago, there were 4 other elements that were kind of discovered that had been predicted in the periodic table, but they didn't really exist yet. And so we just had little placeholders for them. And you can see them here, number 113, 115, 117, and 118. But literally in June of 2016, they were finally named. Okay, and so 113 is given the symbol NH for nihonium, 115 moscovium, 115 tennesseeum, and 118 oganesson. These are named after either geographic locations where these things were discovered or after the countries of origin of the researchers who were working on this. Okay, and so now we have a slightly different periodic table compared to what maybe you're used to. Okay, so now that we've talked a little bit about the periodic table, let me give you a little bit of a description of how you can read or interpret the periodic table. Okay, and so within the periodic table, you have different ways to look at it. Okay, you have what are called the main group elements and kind of the rest of the periodic table. Okay, and so the main group elements contains what's called the S block. And so the S block includes alkali metals and alkaline earth metals. And the P block, which is on the far right side, includes metals, metalloids, and nonmetals, including halogens and noble gases. Okay, the reason these are called the main group elements is because these are the ones that are at the extreme ends of the periodic table. Okay, so all the way on my left and all the way on my right. The way to read the periodic table is all of the S block have valence electrons in the S orbitals, and all of the P block have valence electrons in the P orbitals. Okay, the group number basically tells me how many electrons reside in that energy level. Okay, and so for example, if I have a group number of 1, there's 1 valence electron or 1 electron in the outermost energy level. Okay, and the period number going across tells me the principal quantum number or the n value. So for example, everything in period 3 has its valence electrons in the 3rd energy level. Okay, the middle part of the periodic table contains what are called the transition metals or transition elements. These have d and f orbitals in them. Okay, and so the d block is technically the transition metals, and the f block, which is this little strip on the bottom, is all of the rare earth metals. These are considered inner shell electrons because the energy levels are actually lower than the principal values. In other words, if you kind of scan the periodic table and go from left to right, you might have electrons in the 4s energy level, and then it goes down 1 level to the 3d, and then it goes back up to the 4p. So all of the d blocks go down by 1 quantum number. Everything in the f block actually goes down by 2 quantum numbers. So you might have 5s, but 4d, and then f would be 1 less than that. Okay. So now that you know how to read the periodic table and judge where things are, let's talk about trends in the periodic table. Okay, so what is a periodic trend? Periodic trend is some kind of pattern that emerges. Okay, so in other words, it would be nice if I could just kind of look at the periodic table and predict how certain elements are going to behave based on where they are in the periodic table. Okay, it's not going to be perfect or foolproof, but it'll work reasonably well, right? You get a pretty good idea of how things are going to do or behave based on where they are in the periodic table. And a lot of this was observed experimentally, but then in terms of justifying it or explaining it, you can usually explain this using a relatively small number of ideas. Things like, how many valence electrons do you have? How many core or inner shell electrons do you have? And how many protons do you have? Which is sometimes called the nuclear charge. Okay, so first thing that we're going to talk about is atomic radius. Okay, this is a periodic trend. The atomic radius basically refers to how big the atom is. Okay, even though they're not exactly perfectly spherical, we can still think of them as being little balls or spheres. And even though the electrons live in some cloud, we don't really know exactly how far away they are, we can still talk about, on average, how far away are the electrons from the center, from the nucleus. Okay, so there are certain trends that I want to point out to you for atomic radius. As you go horizontally across, okay, the atomic radius decreases, meaning the atoms get a little bit smaller. And as you go down vertically in a group, the atomic radius actually increases. They get bigger. Okay, and so what I'll do now is show you an image to illustrate this. So here's a graph of the atomic radii for some different elements. Okay, and you can see the trend as I go down. The atomic radius gets bigger and bigger and bigger, from hydrogen to lithium, sodium, potassium, rubidium, cesium, francium. And as I go across any of these periods, the atomic radii gets smaller. For example, if you look at the second period, from lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, you can see the trend, how they get smaller and smaller. Okay, on the top is an explanation of how the atomic radius gets defined for certain nonmetals. Okay, it's really 1/2 of the distance between the two nuclei of adjacent atoms in a molecule. Okay, so for example, this is Cl2. This has a bond between two chlorine atoms. What I want to do is measure the distance between the two centers, the two nuclei, and divide that by 2, and that gives me the atomic radius of just one single chlorine atom. One thing that's possible is you can explain this in terms of what's going to happen vertically and what's going to happen horizontally. Okay, so for the groups, we're going to increase the size as you get more and more energy levels, which sort of makes sense because that means that there's a bigger distance away that the electrons are in the valence from the center or from the nucleus. So that trend as you go down makes sense. The one that's a little bit harder to explain is horizontally as you go across, right? Why should they get smaller instead of bigger? Because after all, you're having more electrons in there. Why shouldn't they get bigger instead of smaller? Okay, the argument is that even though you have more electrons, you also have more protons. And so there's a stronger attraction between the nucleus with all of its positive charge and all of the electrons with all of their negative charges. And they get drawn closer together. Okay, so this is sometimes called an increase in the effective nuclear charge. There's more of a feel that the electrons on the outside are experiencing due to all of these positive charges in the nucleus. Okay, so this effective nuclear charge is a little bit hard to calculate and define, but basically you can think of it as incorporating a shielding effect of all of the inner or core electrons. Okay, so what does that mean? Well, let's pretend that I'm the center, the nucleus, okay, and I have all of these protons inside of me, as well as neutrons, but they don't have a charge, so I don't really worry about them. Okay, the protons that are in the middle have a positive charge, and the electrons that are on the outside have a negative charge. But the electrons that are all the way at the end, right, all of those valence electrons, they don't really feel the full effect of the nucleus. Why? Because in between the nucleus and all of these valence electrons out here are these inner or core electrons, and they act like a little shield, right, a barrier. So they protect the electrons all the way at the end from feeling the full effect of the nucleus in the center. Okay, so they block or shield a little bit, so that the effective nuclear charge is always less than the total number of protons, or the atomic number of that atom. The reason it's hard to calculate or complicated to calculate is because different electrons can have different extents of shielding. Not all the electrons are equally good at shielding things, and you have like variations between different subshells and orbitals and things like that, okay? If you look at the transition metals, right, the D block, things that are in the same period have almost exactly the same atomic radius because the effective nuclear charge is the same, because the number of inner or core electrons isn't really changing. Okay, so now the next periodic trend that I want to tell you about is ionic radius. Okay, so ionic radius is defined in a similar fashion to atomic radius. Okay, it's basically how big an ion is instead of how big an atom is. And we also have a similar trend as you go across that I'll show you in a minute. The more interesting question is what happens to the radius of the ion compared to the radius of the atom. Okay, and so for metals, the ionic radii tend to be smaller than the ones for the corresponding atoms. And for nonmetals, the radius tends to be a little bit bigger than for the corresponding atom. Okay, this kind of makes sense if you think about it, because for metals, they tend to lose electrons when they form ions. And so if they're losing electrons, those electrons are coming from the outermost energy levels. That means that the atom kind of had to lose electrons from the top to become the ion. It shrunk, right? That outermost energy level is gone, doesn't exist anymore. For nonmetals, when they gain electrons, is what they typically do, those electrons get added to the outermost energy level. So it's not that I lose energy levels, and actually that energy level is getting bigger and bigger and bigger because of increased repulsion. Okay, and so that's why the radius of the ion for a nonmetal tends to be larger than the radius for an atom. And what I'll do now is show you a picture to kind of illustrate this. Okay, so here's a graphic that demonstrates ionic radii versus atomic radii. Okay, and so in this picture, all of the atomic radii are in this greenish olive tanny color. And for the metals, which are on the left, the ionic radii are in red. And you can see how, for example, for lithium or sodium or potassium or any of these actually, the ionic radius is smaller than the atomic radius, right? The red circles are smaller than the tan circles. But for the nonmetals, which are on the right, all of the ionic radii are in blue, and you can see how those are actually larger than the ones for the atoms. What exactly is ionization energy? Well, you can think of ionization energy as how much energy do you need to remove an electron from the ground state when something is in the gas phase. In other words, you're starting out with a neutral atom, you're popping off an electron to form a positively charged cation. Everything is in the gas phase, okay? And you can technically do this lots of times. So the first ionization energy would be how many times or how much energy you need to lose an electron the first time, right, from the highest energy level. Or the second ionization energy is to remove the second electron, or the third, or the fourth, or the fifth. Okay, the point is that it gets harder and harder and harder to remove more and more electrons, okay, because you are starting out with something that already has a charge, okay? Let me give you an example. Let's say that you have, I don't know, $10 in your wallet, okay? And your friend asks you for $1. You say, all right, I'll give you $1. It's not such a big deal. But if you only have $2 in your wallet and your friend asks you for $1, he or she has to be a really good friend for you to want to give up one of your $2 to this person, okay? You're less likely to donate it if you don't have that much to begin with. Okay, so that's kind of what's happening. As you lose more and more electrons, you don't want to keep losing more and more electrons, so it just gets harder and harder to get rid of them. Okay. You also get these relatively large jumps or gaps in the ionization energies when you switch from one energy level to another. In other words, for something like sodium that only has one electron in the valence shell, it's not so hard to lose that electron. Because then if you lose it, the energy level underneath it is completely filled. And that's a good thing. That's considered stable and happy. It's got 8 electrons in its now outermost energy level. But to lose a second electron would be really hard because you're breaking up like a really stable situation. And you're also switching from valence electrons to core electrons. Okay, so what's the trend for ionization energy. Ionization energy generally decreases as you go down a group. In other words, it gets easier and easier to remove the electrons as you go down, and it generally increases as you go across a period. In other words, it gets harder and harder to remove electrons as you go across a period. Okay, and so I'll show you what this looks like in an image as well. So here's a graph that shows why these things are called periodic trends. You can see that there's a period or a pattern to the data, right? It goes up and down and up and down and up and down. It kind of follows like that. Okay, and so here is the trend in the second period. Okay, it goes up as you go there, and then as you go down, for example, from the same group, for example, the noble gases, here's helium, here's neon, here's argon, here's krypton, here's xenon, right? They decrease. Okay, and so you can see the trend that as you go down a group, the ionization energy decreases, but as you go across a period, the ionization energy increases. You do get some minor exceptions, for example, here or here, where you would expect that as you go across a period, it should increase, and it generally does increase, except for example, the difference between beryllium and boron, or nitrogen and carbon. Okay, that changes a little bit. There, you have these minor effects due to changes in the electron configurations, right? So if you looked at something like beryllium, beryllium is 1s2, 2s2. Boron has the following electron configuration, 1s2, 2s2, 2p1. Okay, it's relatively easy for boron to lose this electron from the 2p because then it will have a filled subshell rather than a completely filled shell. Okay, same kind of thing happens if you look at nitrogen and carbon. Nitrogen is 1s2, 2s2, 2p3, 2p1, whereas carbon is 1s2, 2s2, 2p2, and oxygen is 1s2, 2s2, 2p4. So this should be 3. So basically what's happening is for oxygen to lose one electron, it would form 1s2, 2s2, 2p3, which is the same electron configuration as nitrogen. And that's considered stable because it's not completely filled, but it's completely half filled. And so that's considered better as well. Okay, and so that's why the ionization energy for oxygen is a little bit less than the ionization energy for nitrogen. Okay, so let's look at some other periodic trends. Electron affinity is basically defined as how much energy do you need to add an electron in the ground state in the gas phase. Okay, and so we're going to start with a certain element in the periodic table and add an electron to it. So it forms an anion. So it's going to have a negative charge instead of a positive charge. Okay, it's not exactly the same as ionization energy, but it's related or similar to ionization energy. Okay, and so you would expect that the trend is the same here as well, meaning that as you go across, electron affinities tend to increase. As you go down, electron affinities tend to decrease. Okay, so trend is pretty much the same, but gets a little more complicated because you have extra repulsions between the electron that's coming in and the electrons that already exist in the atom. Okay, and so just to show you, here's a graph of the electron affinity for the different elements in the periodic table. Okay, so you can see here that this graph looks similar to the one that I showed you a couple minutes ago for ionization energy, but it's a little bit less clear-cut, right? There's still a general increase in electron affinity as I go across. And there's still a general decrease in the electron affinity as I go down, but there are some exceptions. Okay, so the next thing that I want to tell you about is electronegativity. You can think of electronegativity as a tendency to gain electrons. Okay, and so this is related to both ionization energy and electron affinity. Okay, and actually there are different equations that different people came up with, like Pauling and Millikan, to come up with a scale for electronegativities. Okay, so there are numbers associated with electronegativity, but they're not energies like they were for ionization energies or electron affinities, but they're still rated. So you can still rank the relative electronegativities of different elements. Because they're based on ionization energies and electron affinities, they have the same trend as ionization energy and electron affinity, meaning that typically electronegativities increase as you go across, and they decrease as you go down. Okay, and so I'll show you that graphically as well. Here are electronegativities on the x-axis. The symbol for electronegativity is sometimes En, or Greek letter chi, which looks kind of like an X. And on the bottom here, on the x-axis, is the period. Okay, and so you can see the trend that, for example, within a certain period, as you go across the period this way, the electronegativities increase. Okay, and so if you go across a period, electronegativity increases. And as you go down, the electronegativity tends to decrease, meaning that they have a smaller tendency to gain electrons and a greater tendency to actually lose the electrons as you go down. So now, let me shift gears a little bit and tell you something about different properties of elements. Okay, there are different kind of old-fashioned tests and techniques that chemists had used to describe and kind of observe different properties of different elements. One of the most famous ones that actually like a very cool visual element to it is something called a flame test. Okay, and so what you would do in a flame test is literally have your element in solution, and then you spray it into a Bunsen burner, right? The Bunsen burner has this flame, and when the spray hits the Bunsen burner, it actually changes the color of the flame. And very often you get these like very dramatic colors that you can use to identify different metals. Okay, so I'll give you an example of that right now. Okay, here you can see a flame test. Okay, and so this is the normal color of the Bunsen burner. Kind of this bluish purple flame. And then on top you can see what happens if you spray an element on it. I believe this is sodium. And you can see this very bright yellow-orange color that emerges. Okay, and so the point is that every element in the periodic table might have a different color. Back then, they had no idea why they were getting different colors. They were just getting different colors. Okay, now we can kind of explain it because of Bohr's model and other people's developments of quantum mechanics, right? You have these different atoms that have different electrons in different energy levels, and the energy levels are fixed, but they're different for different elements because of different effective nuclear charges and different electron configurations. So when they absorb heat energy, that causes the electrons to get excited, right? So they go up to a higher energy level, and then eventually they come back down. When they come back down, they release energy in the form of light. The light has a certain color or wavelength, and those are the different wavelengths that you see. Redox reactions in this chapter, or this module. Okay, and so the word redox is really a contraction. Okay, and so redox is a combination of a reduction and an oxidation. You say, what are those? Okay, a reduction is a chemical reaction where electrons are gained, and an oxidation is a chemical reaction where electrons are lost. And you say, wait, that doesn't make any sense. Why would a reduction be a gain of anything? Okay, well, you have to think about it in terms of charges. Okay, all of these electrons are negatively charged. So when I gain more of them, I become more negative. Okay, and so in a sense, the magnitude of the charge went down, it became more negative. Okay, we call this the oxidation number. Okay, and so reductions cause the oxidation numbers to go down, to become more negative or less positive. Whereas oxidations, when you lose electrons, get bigger. The oxidation numbers increase. They become more positive or less negative. Okay, and so a redox reaction is really just a combination of a reduction reaction and an oxidation reaction that both happen at the same time. Okay, there's also something called a disproportionation reaction, which is a redox reaction where the same element is being both reduced and oxidized at the same time. Good example of this is hydrogen peroxide, okay, H2O2. So if you look at H2O2, the oxygen in the H2O2 has a charge of -1, or oxidation number of -1. If you leave a bottle of hydrogen peroxide just kind of sitting there on the windowsill or something, eventually it's going to turn into water and oxygen, gas. And so in the water, H2O, the oxygen has an oxidation number of -2, whereas the oxygen in oxygen gas has an oxidation number of 0, right? It's a perfectly neutral element. So the point is that when I go from -1 to -2, the oxygen got reduced, but when I go from -1 to 0, the oxygen got oxidized. Okay, and so it's the same element, oxygen, that's being reduced and oxidized. So that's a disproportionation reaction. Okay, so let's talk about agents. There are reducing agents and there are oxidizing agents. Okay, a reducing agent is something that causes a reduction. So if you think about it, if you're causing something else to be reduced, that means that you yourself have to be getting oxidized. Okay, so this is losing electrons, right? Reducing agents lose electrons. Who likes to lose electrons? Mostly metals. Okay, so metals make very good reducing agents. Opposite scenario, oxidizing agents. Okay, oxidizing agents cause somebody else to get oxidized, which means that they themselves have to be getting reduced. If a reduction is a gain of electrons, oxidizing agents have to be very good at gaining electrons. Who likes to gain electrons? Typically nonmetals. Okay, so these make the best oxidizing agents. Okay, so let me give you some examples of how these things might show up in chemical reactions. Okay, metals can react with different sources of hydrogen ions. It could be water, it could be an acid, to create different ions of those metals as well as hydrogen gas. Okay, and so for example, magnesium might get converted into magnesium ions. Okay, and so Mg might form Mg2+, right? Typical oxidation number for magnesium is +2. But if the magnesium is going to be oxidized, that means I need an oxidizing agent or something else that's going to be reduced. So the thing that's getting reduced might be an acid like HCl. Okay, and so in hydrochloric acid, the H+ ions are going to be reduced to H2 to make hydrogen gas. Or if I have something like calcium metal, Ca, and I add water to it, which I don't recommend you try at home, it's a little dangerous, okay? But if you took calcium and added water to it, you can make calcium ions, Ca2+, and the hydrogen in the H2O will actually get reduced to H2, to hydrogen gas. So here's a table called the activity series, which actually demonstrates how reactive or how active these different metals can be. Okay, and so the way to read this thing, which I don't recommend you memorize this or anything, but the way to read it is anything on top is stronger than anything on the bottom. Okay, and right here is hydrogen. So anything above hydrogen can react with a source of hydrogen to create hydrogen gas. Okay, and so for example, magnesium that we talked about earlier can create hydrogen from something like steam or acids. And something like calcium, which is even stronger than magnesium, can still react with steam or acids, but it can also react with just plain liquid water. Okay, so you can see that at the top of the list here are a lot of the alkali metals and alkaline earth metals. Everything that's below hydrogen, down here, right? So copper, silver, gold, platinum, these do not react with water or acids to create hydrogen gas at all. Sometimes called noble metals, okay? These are considered unreactive because they don't really do anything with respect to reacting with sources of hydrogen to make hydrogen gas, okay? Traditionally, a good way to remember this is think of jewelry, right? If you wear any jewelry, right, what metals are bracelets and necklaces and rings typically made of, right? You have things like copper or silver or gold or platinum, maybe palladium, because you don't want these things to react, right? You don't want to be doing the dishes and then all of a sudden, your finger explodes because you have like some reaction between the metal on your ring and the water that's around. Okay, and so these are typically very stable and don't react with any sorts of hydrogen to create H2. Okay, so let's talk about different properties of different elements. For oxidation reactions, which is the opposite of reduction, most of these oxidizing agents have a tendency to gain electrons. And because we're gaining electrons, this sounds a heck of a lot like electron affinity. So the trend for oxidation is very similar to the trend for electron affinity. Okay, so things that have very high electron affinities are also very good oxidizing agents. Okay, so for example, if you look over here, chlorine can react with iodide to make chloride and iodine gas, or iodine solid, depending on the situation, because chlorine atoms have a much higher or more negative electron affinity than iodine atoms, right? So if you looked up the numbers, the electron affinity for chlorine is negative 349, and the electron affinity for iodine is negative 295 kilojoules per mole. Whereas if you try to do it in the opposite direction and start with iodine to make iodide and start with chloride to make chlorine, that's not going to work. Okay, the energies are going in the wrong direction. Okay, and so this is a good example of how you can predict what kinds of reactions will take place based on where the different things are in the periodic table.